All right, we'll go ahead and get started. Today we're covering chapter 16, which is on random variables. But I guess before I go on, are we feeling okay about chapter 15 and all of the additional probability rules? Okay. So chapter 16, we're still in the land of probability, and we're covering...
Professor,
yes.
before we start, is there a difference between mutually exclusive and independent?
Yes. So independent means if the outcome of one event has no influence on the outcome of the other event. So if events A and B are independent, the probability of A does not depend on the probability of B. So the probability of A given B is just equal to the probability of A if they're independent. Okay? And vice versa. The probability of B and the probability of B given A are the same because the outcome of B is not influenced by the outcome of A. So B given A would have the same probability of just B by itself. If they're mutually exclusive, then that means if one event has happened, the other event is impossible. So if they're mutually exclusive, the probability of A given B would be 0. Okay? And the probability of B given A is also 0, because if A has happened, then B cannot happen. If B has happened, then A cannot happen. That's mutually exclusive. So by nature, if something is mutually exclusive, it cannot be independent. And if it's independent, it cannot be mutually exclusive. Question?
Can you give an example of mutually exclusive that can't happen?
Yeah, so if I flip a coin, the outcome that it lands heads or tails are mutually exclusive. If the coin has landed heads, it cannot at the same time have landed tails. But if I flip a coin 2 times, the outcome of the first coin flip is independent of the outcome of the second coin flip. So whether the second coin flip lands heads or tails is not influenced by what happened in the first coin flip. But if we're talking about an individual coin flip, the outcome that it lands tails is mutually exclusive from the outcome that it lands heads. Yes?
Does that also mean it's disjoint?
Yeah, mutually exclusive and disjoint are synonymous. Okay.
But not independent?
Independent is independent. Independent is not disjoint. In fact, if they're independent, it cannot be disjoint. Yes? I think I took the video. I don't think I've posted it yet, so I'll do that. And it was a short one because the first half of the class was going over the test. Okay, so we'll talk about random variables. Random variables describe, I guess, numbers where we have a random event and we assign numbers to the outcomes. Okay? So a simple example is we could have a coin flip, and right now a coin flip we say the coin landed heads or the coin landed tails. If we want to turn it into a random variable, we would assign a number to the side heads and a number to the side tails. Most likely we would assign the number 1 to one of the sides. So for instance, we might assign heads to 1, and we might assign 0 to tails. So if the coin landed heads, the outcome of the random variable would be 1. If the coin landed tails, the outcome of the random variable would be 0. And so after 10 coin flips, maybe the coin landed heads 6 times. Alright? So the mean of our random variable after 10 coin flips would be 6 out of 10, or 60%, 0.6. So random variables is we have a random experiment or a random trial, whatever you want to call it, and we assign numeric values to the outcome of the experiment. So for example, a coin flip, the outcome could be heads, or the outcome could be tails. Then the value, so I'm going to just call this the random variable x. We might assign heads to 1 and tails to 0. So the random variable x can take on the values 1 or 0. And we might also list off the probability. The probability that the random variable x takes on some particular value x. So we have big X taking on some particular value little x. What would be the probability that it takes on the value heads? 0.5, and the probability that it takes on 0, 0.5. Okay, so that's one example. We could talk about, rolling a die. Then our outcomes, I guess, would be so those are the outcomes that could happen when you roll a die. We might assign the random variable x. We might just say these are the values that x can take. And the probability of taking each of these values would be 1/6. Or perhaps maybe you ask how many siblings do you have? And then so we could just go directly to the values that x could take on. And maybe we have somebody has 0, 1, 2, 3, 4, 5, 6, and we'll just say 7 plus. Okay. So I guess technically you'd have to, for the individual values, it would keep going on, and maybe this would be I don't know if I'm adding these up correctly. Whatever. What does this add up to? 70, 80. Okay, so et cetera, et cetera, et cetera. Okay. So we might, and these again would be the probability that x takes on these values here. Okay. So that is these are examples of random variables. These are all examples of discrete random variables. Okay, discrete means we can list out every outcome. Okay, we might have examples of continuous random variables. So we could select a random person, and instead of asking how many siblings, we could ask how much do you weigh, and the outcome there could take on any value, right? If we have an accurate scale, or a very precise scale, somebody could weigh 136.75 pounds, someone else could weigh 136.78 pounds, and those would be slightly different values. So with a continuous random variable, you would not be able to list out all of the outcomes. Okay? These are all examples of discrete ones. When we're talking about a random variable, we might be interested in what we call the expected value, or the mean. Okay, so the mean of a random variable might be called the expected value. And this would be if you were to record all of the outcomes of an experiment after many, many, many trials, and you just took the average of the numeric outcomes, or the mean of all of them, what number would we see? So with a coin flip, what would our expected value be? So with a coin flip, if it lands heads, it gets 1, and if it lands tails, it gets 0. If we recorded the outcome of thousands of coin flips, and we took the average, what would our expected value be? 0.5, exactly. Okay. What about rolling a die? What would our average be? Okay. Well, here. So we'll talk about finding these things. So the expected value, mu, or we might call this the expected value of x. This is equal to the sum product of each particular value of x that it can take on, multiplied by the probability that x takes on that value. Just want to make sure. So in our case, we would take, so for the coin flip expected value, the outcome is 1, takes on, shows up with probability 0.5, and the outcome 0 shows up with probability 0.5. And so the expected value mu, or e of x, would be 1 times 0.5 plus 0, 0.5. We could do the same thing over here. The expected value here would be 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6, so on and so forth. And when you add all of those up, you get 3.5. So that is the expected value of x. So if we find the mean of a variable, what else do you think we would also be interested in finding? The standard deviation, okay? We're going to first start off with the variance, and the variance is the square of the standard deviation. So the variance, okay, or the variance of x is basically we're taking each value of x and we're finding its distance from the mean. So we take each value of x, subtract off the mean, so you've got to find the expected value first. In order to find the variance, you've got to find the mean or the expected value first. We square that distance, we multiply that by the probability of that, and then we add them up. So that is the variance. And if you want the standard deviation, you would just take the square root of the variance. Okay. So the standard deviation of x is the square root of the variance of x. Okay, so for our coin flip example, I'm going to add another column, and this will be x minus mu, and then I'll have x minus mu squared. Maybe it's overkill here, but so x is 1 and mu is 0.5. So I would do 1 minus 0.5 and I would get 0.5, and I would do 0 minus 0.5 and I would get negative 0.5, and I would take the square over here and I would get 0.25 for both of those. And now I multiply x minus mu squared times the probability of taking on that value, and I add them up. So for the coin flip, the variance of x would be 0.25 times the probability plus for the other value, 0.25 times the probability there. So my variance is 0.25. And thus the standard deviation standard deviation is 0.5. Is that all right? Here, we'll try an example. We'll try another example for you guys to work through. Can I erase this? All right, so let's say there's a, it's like Wheel of Fortune, except we'll make it easy, okay? So you spin the wheel, and we'll say this represents 70%. You win 0. Okay, and over here, 20%. You win $2, and 10%. You win $5. Okay, so what is the expected amount you win? We have the outcome. We should turn this into a random variable x. So we'll say x is the amount we win. So we can either win 0, 2, or 5. And the probability, shorthand we could just write probability of x. This would be 0.7. We take on 2 with probability 0.2 and 5 with probability 0.1. Okay. So the expected amount you win would be 0 times 0.7 plus 2 times 0.2 plus 5 times 0.1. I would get 0.4 plus 0.5. Expected value 0.9. So far, so good? Alright, and then so let's find the variance here. The variance of x, okay, so I'm going to create a column for x minus mu. And then I'll take x minus mu squared. Okay, so 0.9, so here I got negative 0.9. 2 minus 0.9 gives me 1.1, and 5 minus 0.9 gives me 4.1. And then I square it, and I get 0.81 and 1.21, and I can't do that in my head. .81. Okay, and then if I do x minus mu squared times the probability of x, I'd have 0.81 times 0.7. 0.21 times 0.2. And 16.81 times 0.1. And if I add these up, I get 2.49. So my variance of x is 2.49. And so I get that. And the standard deviation of x would be the square root of that. Square root 1.578. Okay. Yes.
What does mu signify in this equation?
Mu is the same as expected value.
Okay.
So mu is the mean. So these are all interchangeable. Mu, e of x, mean of x. Okay? The mean, mu, and e of x, those are all interchangeable when we're talking about a random variable.
Professor?
Yeah.
I think if I remember correctly, there was an easier formula for variance, something like square of expected value minus e to the x squared.
Square root of...
Like, I learned that in math class.
Yeah. No, I know what you're talking about. That only applies for... Hang on, let me think about that for a second. But I'll get back to you. Sorry, I think that only applies in certain situations. But this is the. No, I think that does apply for a lot of situations actually. Okay. Yeah, that one is you take each value. It's x squared. It's the expected value of x squared minus e of x quantity squared. Yeah, you're right. That's valid, and it works. I don't know if it's going to be... In certain situations it'll be easier, and in other situations it will be about the same. Okay. If you want to use that, that's fine. That's fine. Yeah. Okay. If we're talking about combining random variables. Okay, so let's say this is one wheel. Okay. 10%. All right, and let's say there's another wheel. All right, and in this one, you get 0. You win 0 99% of the time. And then here, you win $100 1% of the time. Okay, so the expected value here is what? We would do 100 times 0.1. Here, I'll list out the outcomes. Outcome x can take on 0 or 1, and the probability of x is 0.99 and 0.01. Okay, so the expected value is that plus, oops, 0 times 0.99. So the expected value here is $1. Okay, so in terms of, let's say both games cost $1 to play, which one would you play? So a lot of you would say I'd play this one, right? Because it's got the expected value is even odds, okay? But what about the variance here? Okay, let's look at the variance. So the expected value is that. If I do x minus mu and then x minus mu squared, I would have -1, 0, 1, 0, and then the probability, no, oops. I can just multiply this together and I would get 0.99 and 0. So the, wait, what am I doing? Oh my gosh, this is totally, I'm lying here. I'm like, something is definitely not right. Okay. Thank you.
And then would mu change too?
No, because I calculated the mu correctly. I just didn't write it out correctly here. So the total variance of x is 99.
Isn't mu supposed to be 10? 110.1?
I'm having issues today. 0.01. Because the probabilities have to add up to 1, right? So if this is 99%, this has to be 1%. I am so sorry that I'm just a mess. Okay. And the standard deviation of x would be the square root of 99, which is pretty much 10, but it's not 9.499. I'll just say 9.95. Okay. All right, so let's say you play both games. What is your expected overall winnings? Well, so here I'm asking, oh, you guys are gonna hate me. Let's call this, let's call this one y. Just so we can distinguish between the two. So I'm gonna just change all of these to y's. Okay. Just so we can distinguish one game from the other. Okay, so over here the expected winnings is 0.9 and the variance is 2.49. Over here the expected winnings is 1 and the variance is 99. So if we play both games, x and y, what would our expected winnings be? We would take 0.9 and we would add 1 and we would get expected winnings of 1.9. The variance of x plus y, we would just add the two variances together. And we would do 2.49 plus 99 and we would get 101.49. Okay. So the thing is we always add variances. We don't add standard deviations. So if I want to ask what's the standard deviation, you would first have to go to the variances, combine the variances, and then you can take the square root of this to get the standard deviation. So always add variances, not standard deviations. But something a little funny happens if we change things up, okay? So let's say you could wager, rather than, let's say the game normally costs $1 to play, but let's say you could wager $10, okay? And then it just multiplies everything by 10. So if you wager $10, you would win $50 here, and you would win $20 here. And if you wager $10 here, you would win 0, but you would win 1,000. Okay. That has a major effect on the variance. Okay. So if we're looking at, or can I write this? I'm just going to erase this over here. If we're looking at the variance of some constant times x, that actually becomes a squared times the variance of x. Yes?
So what does variance prove? What does it show?
Okay, so variance, again, is talking about the spread of your distribution here. Okay? So, it's a funny term, but it's just kind of a number to give us an idea of the spread in our winnings. Okay? So if we play dollar, we could win anywhere from 0 to 5 with the spread variance recording to be 2.49. Okay? If we're wagering 10 bucks on one spin, okay, our variance becomes 10 squared times the variance here. Okay, so 10, I could win anywhere from 0 to 50. Okay. And so if I wager 10 bucks on one spin, then my variance for $10 on one spin would be 10 squared times the variance of x. So I would get 100 times 2.49. I would get 249 as my variance.
So do you get anything from 0?
It's my winnings will be anywhere from 0 to 50, but my variance will be 249, and the unit is actually square dollars, which I don't even know what that is, but we see that the variance there is huge. Okay? How would that compare versus I play the game 10 times, each time I wager only $1? What's going on there? There I'm playing the game 10 times, so I'm still wagering $10 at the end of the day, but I'm not wagering it all on one spin. Would I have a greater variance or less variance? Less, right? If I play the game 10 times, each time playing $1, I'm expecting to win sometimes and lose sometimes, and overall my variance would be smaller. I'm not expecting to win all 10 times. Okay, so in that case, if I'm playing the game 10 times, each time $1 on the spin, 10 times $1 each time, then this is not the variance of a times x, it's the my variable. It would be x plus x plus x 10 times, okay? So now I'm asking, what's the variance of x plus x for 10 x's? And then that would be 2.49 plus 2.49 plus 2.49, et cetera, et cetera, et cetera. And my variance here would be 24.9. Okay, so it's much smaller than over here. Okay, and that makes sense, right? If you were to gamble, you could choose to bet all of your money on one thing, and you might win big or you might lose it all. Okay, or you could play conservative and just dole out a little bit at a time, and you are unlikely to win huge, but you're also unlikely to lose it all. And that's what we see here. Means and variances. Oh, is that it for just a 10. Okay, so let's do an example. For you guys to figure out. these fair games are probably the easiest concepts here. Okay, so let's say alright, yeah, you're playing a game. It costs $1 to play. And you will lose with probability equal 80%, or we'll say 50%. Lose with probability 50%. Win small prize worth $0.80 with probability equal to 40%, and win large prize worth $6 with probability equal to 10%. Okay. So this is slightly different. Okay. So let x equal the net winnings or net earnings. Net earnings. So that would be win amount minus cost to play. Okay. So create a probability distribution for x. And then calculate the expected value and the variance.
Is that just 6? It's not 0.6?
What's that?
For the large prize is just 6.
Large prize is 6. It's a $6 prize. It's the giant teddy bear. Okay, what do we get for the expected value?
-0.8.
-0.08, right? Net loss of 8 cents. So the outcome could be lose prize or large prize? Your net earnings, if you lose, is -1, right? Because it costs $1 to play, and if you lose, you gain nothing, so you're down out $1. If you get the small prize, your net earnings is -20 cents. Okay? Consolation prize, you're not losing as much. And then if you win the large prize, your net earnings is $5. Alright? Probability of each one would be 0.5, 0.4, and 0.1. And so the expected value would be -1 times 0.5 plus -0.2 times 0.4 plus 5 times 0.1. Okay, so pretty much these two cancel each other out, and you're left with -0.08. So the expected value, when you play this game, if it costs you $1, your expected earnings is a net loss of 8 cents. So that's how they stay in business. Okay, x minus mu. Alright, so to calculate the variance, I would have to take each x and subtract off the expected value. So the difference here would be -1.08. Wait, no. I'm sorry, -0.92. I don't know how to add here. And over there, I would have -0.12, and here would be 5.08. I square each of these things. As I multiply these out. 'Just a bunch of numbers to add here. .0098 and the standard deviation 1.735. Is that okay? All right. We'll end there. You guys have some homework to do with random variables.